So first of all, thanks for the invitation. And I already got some notes down with interesting ideas from Giorgio, so I'm looking forward to more interesting perspectives. And I thought that I would contribute the perspective from consumer robots, so robotic vacuum cleaner, on this topic of map quality. But first, the corporate slide. I'm from Electrolux, and we work in 3 different areas that we call taste, care, and well-being. I apparently lost the taste label here, which is cooking, taking care of clothes, and doing your home environment, keeping it clean. And I work in the clean part. 3 big brands, you could say, Electrolux, AEG, and Frigidaire. And we sell 60 million products per year, and we have 48,000 employees. And from a sustainability perspective, an interesting thing about us is that the main footprint from our products comes from the usage phase. We have to optimize how we produce our products, of course, but we also work a lot on educating users and making it easier for them to use the products in an environmentally friendly way. So that's a different kind of mindset that we need to have to work with sustainability. And about me then, I work as a manager for our advanced development group in Stockholm for robotics. And advanced development to us means that we have about 3 to 5 years to launch. So we work on prototypes and we do concepts for different software and hardware functions within robotic vacuum cleaners. And I have a background from the KTH Royal Institute of Technology, where I did a PhD. Right now, I actually have the task of recruiting someone in computer vision and machine learning. So if anyone is interested, just let me know. Into the hardware then. This is the robot that I talk on today. And this is the Pure i9 series that we launched in 2017, and we did an update in 2019. And right now we have over 100,000 robots connected all over the world to our service, because it's an internet-connected robot, which means that we have gathered data from millions of cleaning sessions by now with these robots. They are connected so we can do firmware updates over the air, which we do regularly to add security updates, of course, but also add functionality. I don't know if you can see my cursor, but I included a screenshot from the app. And sort of over time, we realized that this is how people want to interact with the robot. You just see it standing there in the charger and you empty it now and then, but people really use the app to start it, to schedule, to see where it has been driving, to add zones and so on. So that is very important to the impression of the whole product. But let me go into the main sensor we have, just so you know the background before we start talking about map quality. This robot was the first one, as far as I know, with a commercially available on a consumer product, a 3D LIDAR on a robotic vacuum cleaner. And the idea is that we have 2 line lasers, infrared line lasers on each side. And in the middle, we have a camera with a bandpass filter, so it can only see the laser light. And to comment on one of the questions here about privacy, the data from the camera goes to an FPGA, so a hardware circuit that just extracts the position of the laser pixels. Mm-hmm. So that's a way to make sure that even the processor doesn't have access to the actual image from the camera. We can only see the laser light. The geometry here means that if we turn on one laser at a time, and in this example, we turn on the left-facing laser, we hit the wall or something, and then we see the image of the laser in the camera. And the x-coordinate of that image is a measurement of the depth of... So here's an example image from a lab platform where we extract the full image. And you can see that we can see the floor, then there's a step in height, and the floor becomes uneven because it's a carpet. And then on the far left, hopefully, you can see two vertical lines that are part of a kitchen cabinet, and there's a small offset in X. That's because the lower part is slightly further away, so you can have your toes there. We get, and you could think of it as sort of a slice through the world, a 2D slice along the laser plane. And some of the things we can see here are the floor line, and we can see a cliff if the floor ends, like at a staircase. We can see obstacles so we don't collide with them. We can also see landmarks, and we use flat vertical surfaces as landmarks for the SLAM system. So that's a single slice, and by translating or rotating the robot when it's driving, we can register all these slices, and we can join them into a point cloud or a line cloud, you could say. And this is an example from our debug tool of a line cloud. And you can see the kind of detail we get. We can see the floor, we can see various objects and walls, and we can also see the height of a threshold, so we can determine if it's safe to climb it or not. So that's the sensor data we have. And on top of that, we have a SLAM system. And as I said, we use flat vertical surfaces as features, and we have an EKF SLAM system. And the Dead Reckoning uses odometry and gyro as a standard solution. And on top of that, we have these flat vertical surfaces as features. And to handle the quadratic complexity of EKF SLAM, we use the Atlas system, where we have a graph of submaps with known coordinate transforms between them. We build in the robot when we're driving around. So that's, you could say, the background of the mapping problems that I will describe now. So when the robot is driving, doing a session, this is the kind of data we can gather. First of all, we get the map, and that's based on the SLAM positions where the robot has been driving. And the blue part here of the map, that's the current cleaning, so where the robot has been going right now. And that's updated live in the app, so you can see where the robot is cleaning. The gray part is the persistent map, and that's sort of straight related to what Giorgio talked about, that we actually gather a persistent map that is the union of all cleanings, so we don't have to reacquire it. We have some kind of base view of what the whole home looks like. The user can add go zones. Those are the green ones that you can use for scheduling. Let's say you only want to clean the kitchen one day, for example. And you can add avoid zones. If you have a problem area somewhere, you can avoid it. But we also gather some metrics. For each session, we gather the start and the end time. We gather the reason for starting, which can be pressing on the UI, it can be scheduling or starting through the app or something. And we collect what happened. How did it end? Did it end successfully? Did we get stuck? Did the user stop the cleaning in the middle or something? The area we cover in square meters, and different kinds of events that happen during the session, like stopping to recharge, different kinds of errors, and if the robot needs to relocalize or not, if we have to sort of stop the cleaning to relocalize. So this is the kind of data, both the map and the cleaning session, that we gather for each cleaning. So by now we have a quite big data set of cleaning sessions that we can look at and learn from. Some challenges then that we are still working on. I would say the first one, directly connected to Giorgio's talk, acquiring this persistent map. Because I agree that if you have a map and maybe you build on it or you improve the quality over several runs, of course, that's a better source than the current map. On the other hand, it's going to become outdated and incomplete. So we need to sort of balance those two things. Rough process to acquire this persistent map. So the first one is that we don't need to joystick the robot around, because the good thing about robotic vacuuming is that we're aiming to get coverage every time. So we are, in a sense, visiting everywhere every time. So there's no special map exploration mode, but we run a normal cleaning, and that's the way we gather the map. And at the end of the cleaning, the robot makes a rough decision if this map from this run is acceptable. And it basically depends on if the robot could find its way back to the charger and dock again without having to relocalize or without having to search for the charger. Then we say that, okay, this is probably a useful map. It's not corrupted. So then, if it's not, we just throw it away. We don't even show it to the user. But if it's good enough to get back, then we add it to the persistent map. And that's what we have on the left here. This gray area is growing over time, and it's the union of all the cleanings. And the blue here is the kind of polygon that the user can add on top of it later. Because we add to the persistent map, but the user then needs to make a decision. When the user is happy with the map, to be able to add zones or even name it, then it will be automatically frozen, which means that we stop doing the updates. So right now, that's of course a very rough method, but we found that it's reliable, and it's a good way to make sure that you don't add zones and then the map starts evolving underneath those zones. Or maybe you have a good map that is sort of approved by the user, and we start ruining it if we have a bad run in the 37th session or something. So right now we freeze it, but of course the drawback is that the robot or the user needs to delete the whole map if you want to unfreeze it. Let's say you refurnished at home, or you are missing one room and you want the robot to go there. So it's a very coarse method to acquire this persistent map that we reuse. So of course we would like to have some more fine-grained metrics for map quality, so we could make these decisions in a more in a better way to save more data. So here's an example map just to discuss map quality. And first you see the blob map. This is my apartment, and it's based on the robot position. And on top of it, I drew a schematic representation of the SLAM features that we have, because they are available to the robot, but they are not shown to the user right now. So this is the kind of map that the robot would build, and it has to decide on map quality on top of this map. And for indoor environments, we have a couple of possible priors that we could use. I guess the strongest one maybe is that walls are usually rectilinear. So if something is close to 90 degrees, it usually means that it should be 90 degrees. We know something about room sizes. So if the robot has been going straight for 100 meters, that's probably an error. You don't expect that kind of room size. We also know some things about thresholds and door openings. They are typically a certain width. They are usually, or if there is a threshold, it's usually combined with the door opening, and there's a special angle to the door blade in the door opening. So there are some things we could say about divisions between rooms that we could use. And we can also learn about common room types. So for example, if you find a bed, then you can expect that room not to be very large, or not the largest one in the apartment. Or in the lower right part here, you can see there's a sort of uneven white island, and that's my kitchen table group. In that, you can expect to also find straight benches that are the kitchen, or maybe have this space for your toes and so on. So there are some things we could learn about common room types that would apply to a lot of indoor environments. So those would be one way to determine map quality, if they fulfill these priors that we have. But map quality, I just wanted to mention that can be different also depending on who is looking. So if the robot or the user is looking, so here's an example where if the robot is climbing into my bedroom over the threshold, there could be a sort of impulse error in the heading. And this map, of course, looks quite bad to the user because it doesn't match your mental picture of your apartment. But it's topologically correct, and it's still useful for the robot because the bedroom is consistent, and when you climb over the threshold, you're back to the hallway and you can continue cleaning. So the robot is happy with this kind of map, so it has a high quality to the robot, but it's low quality to the user because visually it looks very off. On the other hand, if we have a small translation error in the bedroom, you can probably see that suddenly now the bedroom seems to be connected to the living room. So this might look okay to the user because it's very close to my mental picture of the home, but the topology suddenly changed, so it's a big problem for the robot. It's going to waste time trying to get back to the charger through the wall, and we have some fallback to detect this, and eventually we will close this off and go through the doorway, but it might waste some time if you have this kind of map error. So this is very bad for the robot, but it might look perfectly okay to the user. So that's something to think about when we are talking about map quality. Another dimension that I wanted to mention is local versus global map quality. Because this is another run in my apartment where the robot failed to map the bedroom. Maybe I turned it off, or maybe it got stuck somewhere and started slipping, so it had to leave the room or something. So the bedroom is not really mapped, but the other parts are okay. Table group, I know that has a very different shape from day to day because of how the chairs are organized. So that's a part that is very dynamic. So it would be nice if the robot could understand that and maybe freeze the rest, but not the bedroom and not the kitchen, so we can update that. So ideally, we would like to have some good metrics for local map quality, so we could do this in a smoother way and not have the user need to tell the robot if the map is okay or not. So those are some dimensions of map quality that I would like to point at as a practitioner. Then there's a common request that we would like to provide external maps to the robot, which is also, of course, connected to George's talk, that maybe you want to reuse a map that has been acquired earlier, or maybe from some other source that is more precise. So why not make use of that? And some possible sources are, for example, measurement apps that are becoming more and more competent. You could also imagine architectural drawings, and they contain a lot of detail that's not interesting to the robot, but they are at least very correct in terms of scale and angles. It could also come from other robots, or maybe your previous robot vacuum cleaner. So you want to inherit the map and keep all the labeling or the zones or whatever history data that you might sort of want to keep. And it could also come from hand sketches, and of course there's a whole literature on how to handle human-drawn sketches with all the errors and the scale errors and the skews that you can get from that. So there's a whole host of possible sources for these external maps. And it's an interesting and very common request, but of course there are some challenges. I would say the first one is related to map quality, that when we get some kind of external map, we would have to automatically verify it so that it's useful to the robot. And one issue is that it has to be connected, of course, so we can use it to do path planning between all parts of the home, because otherwise we will maybe be requested to go somewhere that we can't reach. It has to be closed so it doesn't extend to infinity somewhere, because that can also be a problem to the robot. Rectify it if it's obviously not metrically correct, or then we need to just extract the topology and have that maybe as a guidance for building our own metrically correct map. So you need to, since it's external input, there is an extra step of verification, I would say. But it would be very interesting for us if there was a standardized map format. First of all, because it would be a safer bet to get our product owners to approve this kind of work package, because rather than chances on a special map format or a special kind of map source, this would mean that we would adapt the system to a standardized map that is hopefully available over time, so it motivates the investment. And another benefit would be that third-party sources, maybe other robots or apps that could produce these kinds of standardized maps. So we don't have to do that part. And that would also, of course, minimize the cost and the risk for us. So we would just allow importing these standardized maps that could maybe be provided by architectural firms or special apps, as I said, or our robots or other robots. So we don't need to do that part. Yeah. That's my quick perspective on map quality and what it means to us, and also some challenges that come up when you're trying to do this thing of not throwing the map away, but keeping it between runs. Then you end up with these having to do this sort of elaborate on what quality do we need, or how much do we dare to evolve the map over time without ruining it, so we get a bad user experience. Thank you, and then I'm open to questions.
Thank you very much. Exactly. Are there any questions? I cannot see any. I see question from Matteo Rossi. I will spotlight you. Please, the floor is yours.
Yeah, thank you. So I have more than a curiosity rather than a question. So you talked about how you keep the robots with a sensor, which are mainly 2D sensor, such as 3D LIDARs, which works in 2D, right?
You mean our sensor?
Yes.
No, it is a 2D sensor in each image, but since we are scanning by moving the robot, and if we register all of those images, then it becomes a 3D sensor. So we have a 3D representation of the world at the end.
Okay, so can you not exploit this 3D-ness to also check if the robot is, for example, going out of boundaries, or, for example, going over a dress and changing his direction and the way the map is computed? So basically doing a step into the 3D world to compute a map into the 2D world.
Yeah, in a sense, that's what we're doing with our feature detector, because we're looking at flat vertical surfaces as features, and then we project them down on the ground as a 2D feature, you could say. But we save some metadata, like where it starts and where it ends, so we can avoid confusing different features.
Okay.
So we take the 3D data and we extract a 2D representation of the feature along with some 3D signature, you could say. And that's because of memory and processing requirements. So we cannot store the whole 3D cloud. We're not doing a 3D point cloud SLAM, but we're doing a 2D SLAM based on the 3D data.
Yes, of course. Okay, thank you.
Yeah, sure.
Thank you very much. So next in the queue is Francesco.
Hi, and can you hear me?
Yes, we can hear you.
Yeah, okay. And I would like to ask if it is possible to link the assessment of the quality of the map to the quality of the cleaning, not on the visual inspection of how good appears the map, but of how good it works for the cleaning, for the final task for which it is used.
Mm-hmm. Do you mean even looking at how much dust you pick up, or so, or more how the localization is going while cleaning?
In a sense, the map is good when the robot cleans well.
Mm-hmm.
Okay.
Yeah. So I think what we could use, and to some extent we are using, is while we are driving around in a known map, so let's say the 5th cleaning session, you can look at the difference or the residual between where you see different features and what you expected. And of course, one high residual is not a big problem. That could be a door blade, for example, that changed, or a box at home. But if you start seeing a lot of high residuals all the time, I agree, that's a strong sign that things are going wrong. And then we could say, okay, is this happening always in the same room, or is it a global thing? Because when it starts happening, that probably means that you got lost there. So I agree. There are some things we could look at to monitor the slam performance while driving, and at least and from there we have to do some detective work to try to figure out what went wrong. But at least we can see that something went wrong, so we don't have to wait all the time until we fail to get back to the charger. So I agree. There's even more we could do there to get a quick clue that something is going wrong.
Okay, thank you.
Thank you very much. Now we have Giorgio. You are in the spotlight now, so everybody can hear you.
So, hi, I'm Magnus, and now my turn of questions.
Yeah.
First of all, thanks for the presentation. I see that there are a lot of points in common that arise from using the maps. When I think about a vacuum cleaning application, if I would have to develop such a system, like in a imaginary world, I would just try to build a system as simple as possible and trying to enforce the interaction of the user. Like, meaning I'd like to say, okay, dear user, you now teach me where I have to go. Like, meaning you teach me the layout of the room. So like, joystick once the robot runs, say, this is the living room, or you press a button, room number 1, room number 2, room number 3. Just to have a system that is as simple as possible, because you don't have any loop closure. You're gonna tell the robot, this is the living room, this is the, all the aspects, and then let it evolve. Like, maybe then, after having provided the robot with this initial knowledge, I would start an automatic run that runs on this platform. I wonder why this hypothesis has never been considered into the many products that I have seen, and if there is any reason. Like, that was my
question. I agree. It's I haven't seen that in any robots. Some have an exploration mode where you press go explore, so the robot optimizes for exploration rather than cleaning, but there's no one that automatically sort of or manually drives the robot around to acquire the map. And I can't speak for other brands, but I know in our case that, first of all, our sort of brand or approach is that we want to simplify the everyday life for people. So we also don't have almost any tuning in the app. There's very little you can change except for the suction power. So the philosophy has been all the time that you should be able to just open the box on Christmas Eve and press play, and it should just work. So that's one part. That's sort of our choice. But another part is that over time I've grown more and more suspicious to users because you're probably spoiled with having PhD students around, right, that are good at robotics. So they understand what it means to joystick the robot around and what the robot needs to see. But I'm afraid that if we start allowing the users to drive it around, they would, for example, help it by lifting it into the next room and taking a look there. Or they would maybe move things that should be in a different place when they're actually running or so on. So I think it's a cool strategy, but it's quite risky if you deploy it to the general public. So that's why we went for this sort of complete autonomy in the robot. We don't expect the users to help out.
Yeah. Perfect. Thank you.
Yeah, you're welcome.
Thank you very much. That was very nice insight in the end. And last but not least, Jan, you are now in the spotlight.
Yeah. I would say that's the $1 million question still. Who are the customers right now? But I would say there's definitely right now. I think we have a bimodal distribution. we have the early adopters, and those are the tech-savvy people who were the first ones to adopt vacuum cleaners. And we hear a lot from them because they are very interested in our forum. They want to know how the SLAM works, so they came with suggestions for new odometry and stuff. And they want a lot of control of the robot, and they want to see more details in the maps and so on. And I think for that group, they would be perfectly happy to do initialization and customize the cleaning, for example. But then we have to trade those for some people who don't even bother to connect the robot to the internet, so they don't care about the maps. They just press the play button and leave the room. So our compromise has been to, because also we don't want to do a lot of features that only 10% of the users use. So we are more aiming towards the broad adoption, people who just want the job done. And I think that means that we have sort of held back on asking the user to do a lot of initial things or a lot of settings in the map, but it's a very common request. So we are always balancing that. Yeah, thank you.
Thank you very much. And we have one more question. So I'm giving floor to Max.
Great, thank you. Thank you again for the presentation. One thing that I stumbled across also in George's previous talk was the standardization aspect. You mentioned briefly that there might be a good business support, let's say, for a standardized map. But I see such wide variety of hardware constraints, especially for vacuum cleaning robots, relative to, let's say, the bigger robots, the logistics robots or something like that, that might, at least have somewhat of a similar use case, getting from A to B. Do you think there is a way to try to, pool this kind of constraints, or is it like just too varied to actually make sense to try to standardize?
Mm-hmm. Yeah, I agree. It's right now it's a big problem because, as you say, I've seen some drafts for map standards, and they don't usually capture, let's say, the signature of different features, for example, that are completely different to our robot than someone who does VSLAM, or if you have a 2D LIDAR that is rotating. So I agree. And I think right now, probably we would use a standardized map, we would import it, and we would use it as a reference, but then we would have to add, and we would have to somehow explore it ourselves to decorate it with the special signature and the type of features that we have. And someone with a VSLAM robot that might be looking at the ceiling, they would have to also drive in this standardized map and connect their special type of features to this map. So probably right now, if you load or if you acquire a standardized map, that's not the final solution. You need to add your own, let's say, layer of your special features. But we are also seeing that the robotic vacuum cleaner segment, they are more and more consolidating towards a few, like the smartphones do, a more standardized setup of sensors. So I would say the group of robots that have a spinning 2D LiDAR on top, they are becoming bigger and bigger. That's becoming almost a standard setup for robots. So in a sense, if you could adapt to that type of robots, then I guess that would be maybe a way to standardize for our segment, that you would provide data that is almost ready for that kind of robot. And if you have a different setup, then you need to add your own signature or your layer of features on top of that. So I think that's the best answer I have right now. But I agree, it would be hard to standardize something that solves it straight away, because we have such a different suites of sensors on different robots.
Yeah, I was thinking, sure, on the representation part for the sensor, let's say, observations that need to be stored in it, but also in terms of computation hardware that you might have on board, needs to be somehow compatible, right? And especially with the consumer robots, I guess the smaller the better, right?
Yeah, but at least I guess Martin is part of this standardization committee, so you'll have to correct me. But what I've seen from the drafts is one type is let's say a feature-based map with line segments, and another one is an obstacle, what's it called, or a grid map with obstacle probabilities. And at least if you have a feature-based line map, I think that kind of format is quite lightweight. So at least for all the cleaning robots I see now that are on the that have some kind of navigation, not the ones that are just bumping around, but let's say second level robots that are becoming more popular. I think all of those could handle that kind of format. And also the trend is probably now that we are lifting computation to the cloud or to the edge. So you don't need the hardware on the robot to let's say map your sensor data to the standard. That could happen in the cloud server instead. So I think computation is less of a concern right now. It's more about not having the right type of features in the map.
Okay. So you would say that the business case also moves towards a little slam box that you might have in your apartment, like Jojo said?
Not the physical slam box, because I think it's very constrained on hardware, but it could be that you hand over, let's say the merging part, you do a run and you try to make some conclusion, how should I modify my persistent map? That kind of computation could be left to a cloud server instead. So we're moving computation from real time on the robot to near real time in the cloud as much as possible to save money on the robot hardware.
Thanks.
Yeah, you're welcome.
Great. Thank you very much. So